Hello everyone, my name is Chris Free and I'm excited to talk with you today about the future of seafood under climate change. Over the next 12 minutes, I'm going to provide an overview of the importance of seafood to human society, the impact that climate change is likely to have on the production of seafood, and the opportunities for adapting ocean food systems to mitigate these impacts. Wild and farmed seafood represent a critically important source of food, nutrition, and income to millions of people around the globe. In 2017, an estimated 59.6 million people were directly engaged in fisheries or aquaculture. Over half of the planet depends on seafood for more than 20% of their daily protein intake, and seafood provides a rich source of micronutrients such as zinc, iron, and calcium, especially in tropical developing countries suffering from high rates of malnutrition. The demand for animal-based protein, and for seafood in particular, is expected to grow as societies become increasingly wealthy, diet preferences shift accordingly, and the human population grows to over 10 billion people by the end of the century. Although historically the majority of seafood has come from wild fisheries, the majority of future demand will likely be met through aquaculture production. This figure from the FAO shows that wild capture production has remained relatively stable since the 1980s. Aquaculture production has grown rapidly and now produces almost as much food as wild fisheries. Given the importance of marine fisheries and aquaculture to feeding a growing human population, there's a lot of interest in understanding how climate change is likely to impact fisheries and aquaculture and what can be done to mitigate any of the negative impacts. Over the next few slides, I'm going to review the impacts of historical climate change on ocean food systems, and then we'll talk about the opportunities to mitigate these impacts through adaptation. First, marine fish and invertebrates are shifting distributions to track their preferred temperatures. This changes both who has access to fishery resources and who has the responsibility to govern them. In this map, the small arrows represent the direction and magnitude of distribution shifts of individual species over the last 50 years, and the big arrows represent average shifts in each U.S. coastal ecosystem. In general, fish have shifted their distributions northward or poleward, or into deeper water to find cooler temperatures. Second, warming has already modified the productivity of marine fisheries around the globe. In a recent paper, I worked with colleagues, including Dr. Kiva Oken, a professor here at UC Davis, to analyze the impact of historical ocean warming on the population growth rates of over 200 fish populations. We found that more populations have been negatively impacted by warming than have benefited from warming, and that these impacts have resulted in a 4.1% reduction in sustainable catch potential over the last 80 years. Unfortunately, these impacts are expected to accelerate with increasing emissions. A really nice paper came out last year that ensembled the predictions of 6 different ocean ecosystem models to establish the most authoritative forecast of the anticipated impacts of climate change in ocean fisheries to date. They forecast declines in productivity toward the equator and increases in productivity towards the poles as stocks shift distributions to track their preferred temperatures. In this figure, projected declines in abundance are shown in red, whereas increases are shown in blue. This inequity in climate impact worsens with increasing emissions, as seen here, with even deeper reds at the equator and deeper blues at the poles. When integrating impacts across the global ocean, they forecast a 4% decline in abundance in the least severe emission scenario and a stunning 18% decline in abundance in the most severe emission scenario. However, human responses to these changes could make the impacts on human society better or even worse. For example, a failure to rebuild overfished fisheries and to account for climate change in fisheries management could result in greater losses in catch than expected from climate change alone. On the other hand, the benefits of reforming fisheries management to end overfishing while accounting for climate change could offset or even outweigh these negative impacts. In the next few slides, I'm going to walk through the reforms necessary to prepare fisheries for climate change and then show the potential benefits of these efforts. First, ending overfishing and rebuilding overfished stocks will go a long way towards both enhancing the ecological resilience of fish populations to climate change and to increasing long-term yields from fisheries under climate change. The FAO estimates that about 33% of global fish stocks are overfished and therefore producing less catch than would be possible if they were fished at sustainable levels. Second, fisheries management will have to account for climate-driven shifts in productivity and distribution through high levels of regional or international cooperation. This animation shows the forecasted shift in the distribution of Peruvian anchoveta, the world's largest fishery in terms of volume, and illustrates the international scale of these two challenges. Here, we see two things happening. First, we see that the distribution of Peruvian anchoveta is expected to shift poleward out of Peru and into Chile. Without international cooperation, what is to incentivize Peru not to fish out the anchoveta before it exits its waters? Second, we see that the size of the Peruvian anchoveta distribution is shrinking, which likely means that the productivity of anchoveta is also shrinking. Detecting and responding to this shift will be impossible without international cooperation that promotes data sharing and establishes clear rules for allocating catch limits in response to distribution shifts. In a recent paper, we examined the extent to which the benefits of such fisheries management reforms could offset the negative impacts of climate change. We found that climate-adaptive fisheries reform, shown as solid lines in this figure, could increase global fisheries catch relative to today under all but the most severe emissions scenario, shown in deep red. A failure to reform fisheries, on the other hand, results in less catch relative to today under all climate change scenarios. However, even the best climate-adaptive fisheries reforms will be insufficient to maintain the per capita seafood supply for a growing human population. Here you see declines in per capita production under all climate scenarios, even with perfect fisheries reforms. This is especially true for tropical developing countries, which in many cases are experiencing rapid human population growth and large negative impacts of climate change. This finding led us to ask to what extent the expansion of sustainable offshore aquaculture could offset climate-driven losses in seafood, even under climate change. In the next few slides, I'll talk through the pathways required to expand sustainable mariculture and will then present our modeling results. The first pathway to expanding mariculture under climate change will be to establish policies that promote sustainable mariculture development. In countries with relaxed environmental regulations, mariculture has grown unsustainably, leading to enormous environmental impacts and ultimately to mariculture collapse. In these countries, stricter guidelines and mariculture best practices will be necessary to ensure sustainable development. In many highly regulated countries, such as the United States, mariculture development has been slow due to complex or overly precautionary regulations. In these countries, the process for permitting sustainable mariculture operations needs to be streamlined to foster sustainable growth. The second pathway to expanding mariculture under climate change will be to invest in technological innovations that increase the efficiency with which mariculture species can be grown, or to increase the tolerance of mariculture species to changing environmental conditions. Currently, feed for finfish mariculture depends on ingredients derived from wild fisheries. This means that the availability of feed ingredients from fisheries places a limit on the production potential of finfish mariculture. Thus, developing new ingredients and technologies for replacing wild fish ingredients would greatly expand the potential for finfish mariculture. Fortunately, this is already happening rapidly within the industry. Furthermore, while selective breeding of livestock for fast growth or other favorable traits is the norm, selective breeding of mariculture species for fast growth has been rare. Evidence suggests that breeding a larger portion for fast growth could more than offset the negative impacts of climate change. Finally, mariculture species could be bred for increased environmental tolerance to allow them to be grown in even the fastest changing waters of the ocean. The third pathway to expanding mariculture under climate change is to promote access to financial resources such as credit and insurance. Climate change is expected to increase environmental variability and the frequency of storms and harmful algal blooms, which collectively threaten mariculture infrastructure and operations. Increased access to credit and insurance would provide buffers against these uncertainties and help promote mariculture expansion. The final pathway to expanding mariculture is to use marine spatial planning tools to locate farms in low-risk areas and areas that present minimal potential impacts in other sectors such as fisheries or tourism. Furthermore, mariculture may even be positioned to enhance ecosystem services. For example, the farming of filter-feeding bivalves may be used to reduce eutrophication and harmful algal bloom risk, and the farming of nutrient-absorbing seaweeds could help prevent eutrophication and blooms before they even happen. I am currently working with a large team of colleagues to understand the potential for these reforms to expand mariculture production under climate change. In this plot, you see historical trends in per capita seafood availability from capture fisheries and finfish and bivalve mariculture. In general, there's been a decline in per capita supply as capture fisheries catches have stagnated and the human population has grown. We found that without fisheries reforms or substantial advances in mariculture feed technology, per capita seafood availability will continue to decline through the end of the century. Here, the dashed line indicates today's production, and bars for mid-century and end-of-century production all fall under that line. However, with reforms and progressive advances in mariculture technology, per capita seafood availability could increase under all but the most severe emissions scenario. I want to conclude by saying that these results are hopeful in that they suggest that the benefits of human innovation could outweigh the costs of climate change. However, these pathways aren't easy and will require a concerted international effort. First, we have to reduce emissions, to reduce inequities and impacts, to maximize the effectiveness and feasibility of reforms, and to avoid surprises that may not be accounted for here. Second, we cannot rely on mariculture to save the day on its own. Reforms in capture fisheries are necessary to limit livelihood transitions and to maximize the availability of feed ingredients. Finally, growth in mariculture will have to be sustainable to limit impacts on marine ecosystems and adjacent industries and will require new and effective governance. Thanks for your attention, and I look forward to the discussion.